All right, this next property of integrals is going to be rather intuitive, I think. So we've got the additive interval property. If f is integrable on AC, so this interval from A to C to B, and also from A to B, we can say that the definite integral from A to C plus the definite integral from C to B should be equal to the definite integral from A to B. So essentially what this is saying is that if you have a definite integral over some vast interval, you could break it up into parts and find the definite integral or evaluate the definite integral of each piece and add it together. This should make sense because it's basically dividing your area up into pieces and then adding the individual pieces together, right? To get the whole entire thing. Think composite shapes. Think of the segment addition postulate from geometry, right? Okay, so let's try that out here on example 8. Use the additive interval property to evaluate the definite integral from -1 to 1 of the absolute value of x with respect to x. So this is one where it would be really hard to turn this into some sort of limit of a Riemann sum that I would have to evaluate. But if I think of this geometrically and think of it in terms of this additive interval property, it's going to make this thing very easy. Okay, so I'm going to draw a graph here of the absolute value function, just this V shape. And then we're going to go from -1 over here to +1 over here. Now nothing's below the x-axis, so nothing's going to cancel out. I just want to find the area of this triangle plus the area of that triangle. And basically what it is that this thing boils down to the definite integral from -1 to 1 of the absolute value of x dx is equal to two different parts. The part over here on the left-hand part, I'll call this one 1. It's the definite integral from -1 to 1. What's this equation right here? This is -x. -x dx plus, and then we have the definite integral from 0 to 1. Stop writing it with a laser. From 0 to 1, and the equation on the right-hand side is just x by itself, not a -1, dx. Right? And then, of course, I would not turn this into a limit of a Riemann sum. Instead, I would just geometrically find the area of each of these pieces. This is a 1 by 1 triangle, so its area must be a half. I got a half plus, I got another half on the other side here to get a total area of 1. So there we go. The value of that definite integral involving something that looked really, really intimidating at first, the absolute value of x, turned out not to be, with a generous helping of the additive interval property together with some triangle area formulas.